Okay, this is basically an IC. This is a 7490 IC. And you can see that this LED display is also an IC. I'll talk about it in a bit. Okay, so the 749 IC is basically a flip-flop inside, just that it is not shown here what exactly goes inside there. And you probably don't need to know that. The only thing you need to know is that this can basically count. So if you want to be able to count, let's say 1,000, 100, 200, and so on, then you need to think what are the number of binary levels you need. So if you want to count just till 2, it will be 0 and 1. You just need maybe just a simple 1 output, right? Because 1 output will give you 0 and 1. Here we want to count 0 all the way to 9. And so what you do is you figure out how many levels you need. So to count 2 numbers, we need 2 raised to 0, so 1 output. To count up to, so 0, 1, to count from 0 all the way to 3, we would need 2 outputs. 1 output, so that will be 2 raised to 1. This will be 2 outputs, 2 square. To count from 0 to, what's the next one? 2 square, 2 cube, 8. So 7, you need 3 outputs, 2 cube. And then here we're interested in counting up to 10, right? So we need to go 0 to 16 or 15, 4 outputs, 2 raised to 4. So you see here that there are 4 outputs because you can now count from 0 all the way to 15, but we don't really need to count till 15. We only need to truncate it from 0 all the way to 9. We don't need anything more than that. So we only need certain combinations of ABCD. We'll ignore 6 of those combinations because they are not needed. So what I mean by that is, if you look at the outputs, okay, ABCD, as I said, we want to count 0 to 9. Just ignore this. So how will you do that? Well, if you have 0, 0, 0, that would be 0 in, that is, you need to convert binary to decimal. If you do this, the next one, that would be 1. This is essentially 2 raised to b plus 2 raised to a. So it's 2 raised to 1 plus 2 raised to 0, which is 3, right? And so on. So you can do that and you can count up to 9. So this is the output of each of these decade counters. Okay. Now, how does this work? Well, what you need to do is you need a clock signal, just like you need it for flip-flops. This is the clock, which goes into, this is just explaining one of these counters, just how this works. So you'll supply this with a clock, and let's assume that it is, well, in this case, it is negative edge triggered, as you saw in the symbol. So every time the clock goes a negative trigger, it will trigger A. Okay. Next one, second trigger, and so on. Now, it turns out that, well, this triggers this one, but it also triggers B, because it is, the circuitry inside is such that that it is triggered based on this. Well, A triggers B actually, so you can see it drops down, so this triggers that. And then here we have the negative trigger is triggering B. Similarly, when this does a negative trigger at B, it triggers a C. So you can think what logic must be inside the decade counter. It's essentially, it should be that the output A should be a clock for B, and the output B should be a clock for C, and so on. And that's probably what is inside the decade counter. There's probably 4 flip-flops which do that, because one clock triggers the second output A and B and so on, but that's not shown because it's too complicated in terms of circuit diagram. Now, this is one piece of it. That is, how do you count from 0 to 9? If you combine 4 of these, like it's shown here, you can actually count up to 1,000. because the first one is going to count 0 to 9 on the first significant, the ones place in a number. The second one is the zeros place, the one place, and so on. So this is basically saying that you have a number which is a 4-digit number. This is going to represent this number. This is going to represent the third digit, second digit, and the first digit. So that's how you will interface them. So that's one part. The second part is you might want to display this on a computer screen or a LED display, right? For that, you need a LED display. Okay, so here is, this is one of, if you want to show a number from 0 to 9, then you'll use one of these LED displays. How will this work? Well, if you want it to show 0, then you clearly need to light. So you need to lighten these. So the number 0 can be shown this way. So you need to light up A, F, B, C, E, and D. If you want 1, then you want to probably light up the 2 ones on the right. So B and C. So what goes in here is that every time you get an output from this A, B, C, D, you need it to light up the appropriate one. Oh, this is. Okay, so here's how you interpret this. You can see this is A bar, B bar, C bar, D bar, which means that this is basically the complement of whatever is there. So if you want to be 0 to be shown, you want everything except G. So everything should be 1. A through T should be 1. So A through E should, just write it down again. So what you need is A, B, C, D, E, F should be 1, and G should be 0, right? Because this is G. It should be, the LED there should not light, which means that if you take the complement of this, then A bar, B bar, C bar, D bar, E bar, F bar should be 0, and G should be 1. This output shows precisely this. It shows the complement. So G bar is 1, everything else is 0. Similarly, if you want 1, then you can see that P and C should be 1, which means the complement should be 0. Let's see here. And so you see that 0 because complement is 1, everything is 0. So that's how the truth table is written. And in order to do this, you have seen this before. If you have a truth table like this, you can then figure out the logic by using the sum of products or product of some rule. So you can figure out the logic yourself and then hook up the right number of logic gates to build it up. Okay. Now the problem is that this is pretty complex, that building that logic gate in circuit on a breadboard is going to take you a lot of wiring. So what they do is they provide you with this IC. I have it somewhere. It's actually a 747 BCD decoder. It basically is wired up so that it will take this output and light the correct LEDs on this number pad. And so you see the right number. Okay, so I showed you this. This is counting tens. Each of these decade counters count 0 to 9. This is the table I showed you, how it is triggered by the clock from clock. Then the clock for A is the output A is the clock for B, and the output from B is the clock for C, and so on. This is the IC. So if you want to use a decade counter, you need to buy the 7490 IC. Okay, now let us look at the pinouts. The input A and BD, so A is here and BD is here, are basically the clocks. Okay, the outputs are Qs, QA, QB, QC, QD. We had 4 outputs, A, B, C, D. And those are the ones which you will use to interpret ABCD. There are Rs, R. Now these are used to reset the Q0, QA, QB, QC, QD. And then this is not a passive circuit, it's an active circuit. So you need to connect this to ground and VCC. And then this NC is not connected. And I think we talked about all these. So that's pretty much it. That's how the IC is to be used. Okay. What is the VCC? This is something we need to see the spec sheet, usually 15 volts, but you need to see the spec sheet to see what voltage you supply. So this is how you will use a decade counter in this particular way. This is the pinout. I showed you this. This is basically saying that this is the output from the decade counter. It can be converted to this output to show on the LED display using the 7447 7-segment decoder. I have the circuit, the pinouts for that. Okay, so we have lamp test. Lamp test is here. Lamp test is 1, no effect, 0, every output is active. Now, this is used so that, I guess it's like a test. There are 7 of these LEDs. So if you set it to 1, sorry, set it to 0, my bad. Then every output is high, which means that you will see the number 8. That's what it means. RB output, avoid showing leading 0. Okay, so RB is used so that you have 0, 1, 2, 3. You don't want to show 0, 1, 2, 3 because 0 has no meaning. So this will, by setting RB input high, you will avoid it from showing the leading 0. Okay. Other than that, we have BCD. So that will be connected to your decade counter, the 7490 chip I showed you. And then this is going to be the corresponding output. So this wiring has been done for you. All you have to do is connect the LED display to this output. And then this goes to 7490. And this goes to the LED display. So depending on what your what you supply to 7490, you will see the corresponding LEDs lit on the LED display. Okay, that's all to it. Again, there's a VCC ground because it's an active circuit. These are your inputs from the 7490, and those are the outputs. Okay, so that's the pinout for the LED display, the decoder. Okay, so that's okay. It's used for switch debouncing. Okay, so let me motivate this with an example of why you would need a Schmitt trigger. Okay, so consider that you have a 5-volt supply which is supplying current to this resistor. Okay, so what you want to do is you want to have a switch here. And so that you want to measure the output across this point and the ground. Okay, so what you do is you basically close the switch that completes the circuit. You get a certain output, VA. So if you close the switch, the voltage drop across this is 0. So you'll see a voltage of 0. But if you keep it open, then you'll probably see 5 volts, right? You see 5 volts because the voltage across this and ground is 5 volts when it is open circuit. Now, what happens in reality is this: when you close this, so let's measure the voltage A as a function of time and the act of closing the switch. So when the switch is open, as I said, voltage is 5 volts. And why is that? Because current flowing through the circuit is 0. So the voltage here is the same as voltage here, which is 5. But that voltage is measured with respect to ground. So it should be 5 volts. Okay, so this is open switch. Okay, now let's close the switch. When you close the switch, what you will see is that it actually, this is 0. So it's expected to go to 0 because once you close the switch, current flows from 5 volt to ground, and the voltage drop between VA and ground is 0. This voltage is going to be 0. So you'd expect that it go to 0, but it doesn't go to 0. It actually bounces back and forth. Okay, and that's because this switch here, there is it develops a voltage, contact voltage, and that basically causes a debouncing. And so it sort of goes back and forth and then stabilizes. Now this is really bad. Let's say, so switch closed. And this part is the transient, which is not good for the person who's closing it, but also not good for the circuit. So what you need to do is you need to take care of, well, you need to ensure that you don't see this debouncing. And so what is done is a Schmitt trigger is used. A Schmitt trigger is a circuit which basically uses hysteresis to avoid this problem. So a Schmitt trigger prevents this debouncing. Okay, a circuit diagram for a Schmitt trigger is like this. This is the input. This is the output. And then there is a hysteresis loop shown inside the triangle. So what's the Schmitt trigger does is the following. If you look at just draw a new page. Okay, so this is how the Schmitt trigger works. Let's draw the input. Okay, now let's say that the input is actually not a voltage level, but it's like an AC signal where it is some curve. Okay, now the Schmitt trigger has two triggers. There's a low threshold and high threshold. So let's say that this is the high threshold, this is the low threshold. High threshold. This is the low threshold. Okay, and then remember that this is the input to the Schmitt trigger. So what the Schmitt trigger does is when there's an increasing voltage signal like this, it uses the high threshold to turn on. So it turns on the high threshold. But then when the voltage decreases, it no longer uses the high threshold to go down. It will use the low threshold to go down. So it will keep this. So it uses not only the value, which is this, but it also uses the kind of signal, input signal, that is, it's increasing or decreasing to figure out when to turn high or low. So the output is okay. So an example of how this might be used in a circuit is like this. here is resistor. In an example, we had resistor and a switch. And this was the output. But instead of connecting the output directly, taking the output, you pass it through the Schmitt trigger. That's all. So this output now is going to be something similar to this. There won't be any debouncing. You just go up and down depending on switch is open or closed. Yeah, so you can search for a Schmitt trigger. I did not quite do that research, but you should be able to buy a Schmitt trigger for use in the device if you want to use that.